Hi there, welcome to Peppy's Civil Class. Today we are going to look at a question under law of conservation of matter or mass, which is also known as the continuity equation. And the law of conservation of matter or mass states that matter can neither be created nor destroyed, but it may be transformed by a chemical process. Okay, so the fundamental equations of fluid mechanics, we have the law of conservation of matter, the law of conservation of energy, and the law of conservation of momentum. Okay, today we are looking at the law of conservation of matter, and we are going to solve this question under the continuity equation. So example 1, it says pipe 1 has a diameter of 75 mm and a mean velocity of 3 meter per second. Then pipe 2 has a diameter of 50 mm and 25% of the total discharge. And pipe 3 has a diameter of 40 mm. We are to determine the mean velocities and the discharges of water in each pipe coming from a junction. Okay, so first of all, let's sketch our pipe. Then we know the data given. Okay, so the discharge entering the pipe 1, then we have the one leaving to be pipe 2, this one to be pipe 3. Okay, so from the data given, it says pipe 1 has a diameter of 75 mm, then a mean velocity of 3 meter per second. And pipe 2 also has a diameter of 50 mm and 25% of total discharge. So Q 25%. Okay. Then the pipe 3 also has a diameter of 40 mm. If pipe 2 is having 25% of the total discharge is 100%. Okay, so if pipe 2 is having 25% of it, then meaning pipe 3 is having the remaining percent, that is 75%. Okay, so solving, we can say that the total mass flow into the junction is equal to the total mass flow out of the junction. Okay, total mass out of the junction. Okay, now the mass flow is denoted by density times discharge. Okay, so now the mass flow into the junction is equal to the total mass flow out of the junction. Therefore, we have density 1 Q1 is equal to, out of the junction you have density 2 Q2 plus density 3 Q3. Okay, but since the flow is incompressible, the density is constant, which is equal to 0. When we say a flow is incompressible, an incompressible fluid is a fluid whose volume or the density does not change with pressure. Okay, so since it's not changing with pressure, meaning it's equal to 0, therefore density 1, it will be equal to 0, 2, and 3. Okay, now you are going to have Q1 equal to Q2 plus Q3. That's our discharge, and discharge is equal to mean velocity times cross-sectional area. Q is equal to VA. Now the question wants us to find the mean velocities and discharge of water in each pipe, okay, coming from the junction. So we're going to do it for each of the pipes. Okay, so in pipe 1, okay, in pipe 1 we have Q discharge 1 is equal to mean velocity 1 times the cross-sectional area 1. Now we know our mean velocity of pipe 1 to be 3 meters per second. So 3 times the cross-sectional area. We don't know the cross-sectional area, but we know the diameter. So we can use the diameter to calculate for the area. So we have pi times d1, diameter 1 squared over 4. We have 3 times pi d1, which is 75 mm. Have to convert it into meters, so we have 0.075 squared all over 4. 3 times this one, we have 0.013 meter cube per second. Okay, so that's our discharge for Q1. Yes, now we have to find our discharge for Q2, but Q2 is 25% of the total discharge. Okay, Q2 is 0.25 of the total discharge. So Q2 is equal to 0.25 times the total discharge, which is equal to 0.013 Q2. You're going to have 0.00325 meter cube per second. Okay, same as the Q3. Okay, let's finish this one, the Q2. So Q2 is equal to mean velocity 2, cross-sectional area 2. Now we know our Q2 to be 0.00325. Okay, it's equal to, we don't know our mean velocity 2, so V2 times our A2, that's our cross-sectional area 2, but we know our diameter for pipe 2, which is 50 mm. Therefore we have pi times 0.050 squared all over 4, and this is going to give us V2 times 0.00196 meter squared. Okay, we have 0.00325 here. Making V2 the subject, we have 0.00325 dividing 0.00196. Okay, now V2 is equal to 1.6 meter per second. That's our V2. Now we calculate for Q3, discharge 3. Discharge 3 is also 75% of the total discharge. That's what we said here. 75% of the total discharge. So we have 0.75 of the total discharge. Now Q3 to be equal to 0.75 times the total discharge, which is 0.013. Okay, and we're multiplying, we are going to have 0.0975 meter cube per second. With this information, we can calculate for our V3. So Q3 is equal to mean velocity at pipe 3, cross-sectional area at pipe 3. We know our Q3, which is 0.0975 equal to V3 times E3 pi times, we know our pipe diameter 3 to be 40 mm, so straight away 0.040 squared divided by 4, right? We're going to have V3 times this expression will give us 0.0126. Okay, then 0.0975. So now we have to calculate for our V3. Okay, let's make use of our sheets. All right, so 0.095 is equal to V3 times 0.0126. Now we have to make V3 the subject and calculate for V3. Now making V3 the subject, V3 is equal to 0.0095 0.00975 dividing 0.00126. Okay, now V3 is equal to 7.7 meter per second. Okay, Q3 here is 0.0. Sorry, the discharge 0.75 times 0.13 is 0.00975. Okay, so 0.0095, 0.00975. Yeah, so we are right here. 0.00975 and 0.00126. Okay, then the velocity at pipe 3 is 7.75 meters. Now, yes, we are done, but let's try to arrange it nicely. So the mean velocities and discharges, okay, coming from each pipe as follows. So pipe 1, we have a velocity equal to 3 meter per second. It was already given in the question, 3 meter per second. And the discharge for pipe 1, discharge Q, we had 0.013 meter cube per second. Pipe 2, we had a velocity of 1.6 meter per second, and a discharge of pipe 2, where is that? Here, 0.00325 meter cube per second, right? Yeah. Then pipe 3, we have the mean velocity here, the mean velocity to be 7.7 meter cube per second, and the discharge, which is Q3, to be 0.00975. Okay, 0.00975 meter cube per second.